Hello everybody, today we're going to talk about the work energy theorem in the context of straight line motion with varying forces. In the previous video, we introduced how to determine work using calculus with varying forces, like spring tension. And by the end of the video, we will work through a problem that combines the idea of the work energy theorem, friction work, and spring work. And so far, we've covered the work energy theorem when an object moves in a straight line under a constant net force. We found that the total work is equal to the change in kinetic energy. As you can see here, work total equals final kinetic energy minus initial kinetic energy. However, is this still true when the forces vary with precision? From what we know, energy cannot be destroyed or created, so from our instincts that that energy should be conserved and that this could be true. Let's prove this by using the work integral. And we have our work integral right here. We'll create a new page so we can work through this process. So we have our work integral, so work equals the integral from x1 to x2 over a force times the segment of x. And so we have this idea from the previous video where we had this varying force and we would segment each part of this line to find its work as the area is work, so you get force times the d of x, and we would make these segments smaller and smaller and smaller and sum them up from point x1 to x2, and that's how we found the work. But as you can see, this is approximately constant to the force is approximately constant, but since we know from Newton's law that force equals mass times acceleration, because we can't use force here, um, when we're taking a derivative from using the x variable, we have to get to velocity where you have like dx over dt. Because this force is not going to be accounted for in this integral, we need to find a way to factor it out, and that's why we use Newton's second law of force equals mass times acceleration, or the net force. To be more specific, this is the net force. And however, now that we substitute force in this integral, we find that the acceleration is also not accounted for. So you have mass times acceleration dx. So we, we will need to substitute it out, and we'll be using the chain rule to write it in terms of velocity. And how we're going to do this is we're going to write acceleration equals dv dt, as we remembered, and we multiply this by dx over dt, or I mean dx over dx, which will, as you can see, velocity over dx, that's what we're, no, it's dx over dt, that's our velocity. So we're going to write acceleration equals dx over dt times dv over dx. And as you can tell, if you look back here, we can already see that our dx is going to be eliminated, which will change the integral to velocity. So we have acceleration equals, this is a t right here, velocity times dv over dx. And so we'll substitute this acceleration and we'll get total work equals from v1 to v2, and we will write it as velocity we can, oh yeah, the mass is constant, so we can take out the mass right here, and we'll have dv over dx times dx. So this cross out, as you can see, and we'll be left with the derivative of velocity of the segment of with respect to velocity. So if we take this integral here, we will get let's give us a little bit more space here. So you'll have 1 over 2 v squared, and then we'll have to plug these in into our velocity here, and you'll have your mass on the outside. Let's bring this over here, which will equal 1 over 2 velocity second minus 1 over 2 velocity initial, all times a mass. So you put the mass on the outside, and as you can see, once we multiply each part by its mass, this is actually the work energy theorem from before, because we know that kinetic energy equals 1/2 mass times velocity squared. Now that we know that it tells us that the work energy theorem is valid even without the assumption that that there's a constant net force. We will apply this concept of work energy theorem to Hooke's law in our next practice problem coming up here. So let's say we have an air track glider. So we'll draw one here. So first we'll draw the track. We have and there's going to be like air pushing out of here, which creates like almost frictionless surface on an object that sits on there. And then you have your air track glider sitting on here. And the mass of this air track glider is equal to 0.100 kilograms. And it's attached to the end of at the end of the horizontal air track by a spring that has a force constant of 20 Newton meters. So we'll draw the spring here, and it's attached, as you can see. So our force constant is equal to 20 Newton meters. Now it tells us that the spring is initially unscratched, and the glider is moving at a velocity of 1.5 meters to the right. So v initial equals 1.5 meters per second. So you have your direction of velocity. And then it asks, find the maximum distance that the glider travels to the right. So that means it's going to reach its final distance when the velocity is equal to 0, because it's not going to be moving anymore. So we'll write from here to here will be our distance d. In the first case, this air track will be on, so there's no friction on our object here. So we'll go to our, as we can see, there's changes in velocity, so we know it has to deal with this right here. So we have work. First, let's move this image, make this image a little bit in the corner here. So we have work total equals k kinetic energy final minus initial kinetic energy. And as you can see, because the velocity is 0, there's the kinetic energy 0 as the object stops at that moment in time, which checks out. Now we need to associate this with the distance, and we know from our how to find the work of spring energy. It's 1 over 2 k force constant distance it stretches squared, and we know that the initial is 0 because it starts from its unscratched position and then it scratches to a certain point, and that's going to be our d value. And if we look back at our work total, this is part of our work total here. So we have our all the work that is going to be applied to use our work energy theorem. So we have 1 over 2 k, and then you have squared second x equals to the minus of the kinetic energy, which is 1 over 2 meters, or not meters, mass times velocity squared 1 as the second one crossed out. And what we're trying to find is the distance d, which is the x value. We'll replace that with d so we can get an idea of what we're looking for. We're trying to find d. So we know we can just cross these guys out because they're going to be the same here. And then we have d equals negative mv squared over our force constant. And this, oh yeah, I just realized, because this is the work of the spring, it's being pushed, it's pushing in the direction of displacement, which means it should be positive here. Like the signs are switched as it's in the direction. This is the work being on the spring, which will bring us to where a positive value here, because you can't take the square root of a negative number. So the reason that it's like that is because it's the work of the spring, which is opposite direction, and that it's pushing the object. So you have d equals mass, which is 0.100 kilograms, times velocity squared, and then over our force constant, which is 20 Newton meters, as you can see here. Now let's calculate that out, and we should find a d value of square. You can take the velocity out if you don't want to take the square root of it and move its power of the 2 and just have it to the power of 1. So you have 0.1 divided by 20, the square root of, and then you times by 1.5. And that gives us a displacement of 0.106 meters. So this is how far the object travels when there's no friction on the object. Now, in the second case, let's say that the air is turned off from our thing here. We will erase this so we can find this a lot easier. So we're going to say that the air is off and there's going to be friction on this sled as it moves. So that means we're going to have a friction coefficient of here, if I can write on the mouse, which equals 0.47, and that's how we're going to be looking at it. we'll draw a free body diagram to, because we're dealing with friction forces, we have to deal with the idea that we have forces acting in different directions. So we have this friction force that's pushing the sled back. And as before, we're trying to figure out how far this thing's gonna go. So we have this normal force, and what's pushing it down is gravity as it comes to a halt. So we find that there will be work of friction as it's a force over a displacement. We can assume that. So it has F of K, but what is that equal to? We can find it from here. So the friction of kinetic energy equals the normal. Well, it's the friction coefficient times the normal force. But what is the normal force? That's unknown. We can know that the normal force is always equal to the force of gravity, which is mass times g. Those are both knowns, which is what we like. So mass times g. And then we have our work from the spring, which is pushing as before. It's exactly the same. So spring equals, it should be 1 over 2 x, no, it's our force constant, x squared final minus initial. But as we looked, x1 starts at 0 and x2 ends at d. So that's what we're trying to find. We know that this work of the spring is always opposite in direction. So imagine the signs are flipped here. 1 over 2 k x1, which is 0. We'll have a change color so you can see, equals 0. And we'll use our work energy theorem from before. So you have work total, which is the sum of the friction work and the spring work, equals the change in kinetic energy. And you already know that it's going to be the final, which is going to be 0, minus the initial, which is going to be whatever the value is going to be. So we're going to have work of the friction. Let's move this up here so we have some more space. So we have work of friction, which is going to be negative since it's acting backwards, as we can see. So you have work spring minus, and then you have the work of this friction equals to the negative of our kinetic energy here. So that'll leave us with a negative of our friction coefficient times mass times g. This is from our friction here. And then we'll have our our minus of our spring work right here. And we're trying to find d, which happens to be this x right here, which is the change, how much it changes. And I'm assuming here, yeah, that makes sense. And then we'll have negative 1 over 2 mass times velocity squared initial. And now let's try to solve for d. So we can get them on one side. But I think we're missing something here. if I can recall, it's, yeah, I see it now. So this is just a force, but work is defined as a force times a displacement. So that means there must be a d value that's associated with this. So let's move this over to the left. So we're gonna have a d value right here, which is the displacement from the work of the friction. And I think you can already tell here, but we're gonna have a quadratic formula to solve for our d value, which is not the most fun things to solve for. I'll have it pre-calculated so I don't have to take the time to solve for it, but you guys can check if you get the same answer at the end. So obviously we're gonna have to get them all on the same side here. So you would write it like this, plus this, and then minus 1 over 2 mass times V1, 2 equals to 0. And we'll use our quadratic formula. So D equals, and if you remember, this is B, this is A, and this is C, and the D's are not included. That's what we're finding. So you have negative B, which is the friction coefficient. Let's move things a little bit more to the left so you don't run out of space here. So you have negative B mg, and then you have plus or minus, but it should be positive because we're not accelerating to the left. As you can assume, that would be true. And then you have B squared right here. So you have the friction coefficient. And then mass times G minus 4. And then it's going to be A, so it's going to be 1 over 2 K times the negative of 1 over 2 mass times V1 squared. You can kind of tell that, oh, that's rough right there. This is going to be 1 over 2 m v squared 1. And we can tell that these kind of just cross out here if you want to just do that. And you have 2 times 1 over 2 k as our a value. These two cross out right here. And now just solve for d. Plug these into your calculator. And alright, and now that you solved it, you should have got 0.086 meters as our distance that the object was able to travel. And thank you for watching my videos. Please like if you enjoyed the video so that I'm motivated to keep making these, and have a good day.